imagine you have a convergent sequence n converging to the point A. Now observe that what this means is that the sequence gets closer and closer to A. So if A were to be here on the number line, then eventually all the terms an will be in any pre-specified interval around the point A. So after a point, all the terms of the sequence have to be here. All terms have to be here. Now, how far along the sequence you have to go to make sure that all the terms in the sequence are indeed in this pre-specified interval depends on the particular sequence. But nevertheless, it is always the case that whenever you have a convergent sequence, all the terms have to cluster around this point A in any pre-specified interval. What this means is that since the points are clustering near A, they have to get closer to each other as well, because if you specify this preset interval to be of epsilon width, that means after a particular point in the sequence, all the terms are within 2 epsilon width of each other. If all the points are here, you can see clearly that the terms have to be at the max 2 epsilon close to each other. This is what is known as the Cauchy property of a sequence. We will define it precisely now. Definition. This is the definition of a Cauchy sequence. Let an be a sequence. We say an is Cauchy if for each epsilon greater than 0, we can find n epsilon in the natural numbers such that if n is greater than n epsilon, then so far it looks like the definition is exactly the same. So what we want to say now is not just that if n is greater than n epsilon. What we want to say is we want to sample two different points in the sequence beyond n epsilon. So we choose n comma n greater than n epsilon. Then mod an minus am will be less than epsilon. So what this is saying is precisely what is illustrated in this picture. If you can choose n epsilon in such a manner that if you sample 2 points, any 2 points of the sequence that lie beyond n epsilon, then they will be epsilon close to each other at max. Then such a sequence is said to be a Cauchy sequence. Okay. Now we'll immediately prove a very simple proposition. This should be reminiscent of a similar property that we had established for convergent sequences. Any Cauchy sequence n is bounded. Now the proof should also remind you of the proof that convergent sequences are bounded. The proof is almost exactly word for word the same. Proof: set epsilon to be 1, and choose n1 as per the definition of a Cauchy sequence. Okay. Now I have to tell you a candidate upper bound for the sequence. Set m, not just upper bound, candidate bound for the sequence to be mod a1, mod a2, dot 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 1 plus mod an plus 1. So I go all the way up till mod an1, then I add another term to this collection, that is 1 plus mod a n1 plus 1. Okay, this is a subscript n1 plus 1. So this n1 plus 1 is there as a subscript. Okay, there's a modulus here. Okay, why does this work? This seems like a weird choice. Well, it follows immediately from the way we have chosen n1. If n is greater than n1, then we know that mod an minus a n1 plus 1, this has to be less than 1. Why is that the case? Because we had chosen epsilon to be 1 and chosen n1 as per the definition of the Cauchy sequences. That means whenever small n is greater than n1, small n comma m is greater than n1, the difference between an and am in absolute value has to be less than epsilon. That's the way capital N1 was chosen. So we must have an minus a n1 plus 1 modulus should be less than 1 because both n1 plus 1 and small n are greater than capital N1. Okay. Now in other words, mod an is less than 1 plus modulus an1 plus 1. Okay. This immediately shows that mod an is strictly less than m for all n in actually I should put less than or equal to m for all n in the natural numbers. By the very choice of capital M, this has to be true. So this proof is almost word for word exactly the same as what we saw for convergent sequences. Now, the definition of Cauchy sequence came from our intuition from the fact that convergent sequences, the terms of the sequence must cluster towards the convergent point A, therefore must cluster towards each other. Let's prove that formally, but there is an interesting twist. Theorem. A sequence An is convergent if and only if it is Cauchy. One direction is palatable. That's how Cauchy sequences were in fact defined. It would be a travesty if it turns out that convergent sequences are not Cauchy. But the converse is also true. Cauchy sequences are convergent. Okay. Now the first part, as you can expect, one direction will be easy. So suppose An is convergent. Our goal is to show that it is Cauchy. Okay. Fix epsilon greater than 0 and choose n epsilon such that if small n is greater than n epsilon, then mod an minus a is less than epsilon. So suppose an is a convergence an is converging to a. Let me just change that for extra precision. Converging to a. Okay. So all we have done is we have chosen the element n epsilon such that if n is greater than n epsilon, mod an minus a is less than epsilon. Okay. Now what we do is, why waste our efforts in thinking? Let's just see what will happen if I choose n comma m both to be greater than n epsilon and then consider their absolute difference, mod an minus am. Okay. Now I need to compare an and am. It's not really clear how I do that, but there is only one way to do it, that is to introduce the element a. So this is less than or equal to mod an minus a plus mod am minus a. I've just added and subtracted the limit a. But both n and m are greater than n epsilon, and n epsilon was chosen so from the definition of the convergence of an to a. So this will have to be less than epsilon plus epsilon, which is equal to 2 epsilon. Okay, and this combined with the k epsilon principle now shows n is Cauchy immediately. Okay, now the converse is a bit involved because we want to show that the sequence that is Cauchy is automatically convergent, and the definition of convergence involves this point limit a. and given an arbitrary sequence, it's not clear how to determine the limit. There is no algorithm for finding out the limit in any easy manner. So let's start the proof. On the other hand, suppose an is Cauchy. Take a Cauchy sequence. We need a candidate for the limit. Okay, but how do we get this candidate? Well, think about it for a moment. If the sequence an were to be convergent, then we already know that any subsequence of an must converge to the same limit. So what we will do is we will invoke the Bolzano-Weierstrass theorem to say that there must be at least one convergent subsequence, and whatever the limit of that sequence is, we will take that as the candidate limit and then reverse engineer and try to show that the whole sequence an itself converges to the same limit. Okay, so we need a candidate limit. Okay, so what we will do is, as an is bounded, that's what we just established in the previous proposition, the Bolzano-Weierstrass theorem says some subsequence say a and k converges to some limit a. Okay, so our goal is now to show that claim an converges to a. Now, how are we going to show this claim? Well, that's not really hard. Recall that a subsequence is a sampling of the sequence in the same order, right? So what this has shown is that after a particular point, there is at least some elements which get really close to A. But Cauchy sequence says that if you go along the sequence, all the terms cluster along each other. So what we use this subsequence as an anchor to make all the terms cluster around terms of the subsequence. But since the subsequence converges to A, all the terms of the sequence must also cluster around A. This is basically a rough and loose idea as to what I'm about to do now. Okay, so fix epsilon greater than 0. We have to find a candidate n epsilon. What we do is we can find n epsilon such that if n comma m are greater than n epsilon, then mod an minus am is less than epsilon. This is the very definition of a Cauchy sequence. Now, since a and k converges to A, for k suitably large, mod a and k minus a is less than epsilon. Okay, now we may choose nk greater than n epsilon. Remember, since a and k converges to A, all the terms in the sequence must be close to A for k suitably large. In particular, if you choose k to be extremely large, we can make nk greater than n epsilon as well. Okay, now mod an minus am, so this is now the central trick of the day, is less than or equal to mod an minus a and k plus mod a and k minus a. I'm using this nk to anchor the sequence, terms of the sequence. Okay, now because nk has been chosen so that mod a and k minus a is less than epsilon. Oh, just one moment, I made an inadvertent error. Okay, what I want to say is mod an minus a. See, I've already dealt with mod an minus an, it's less than epsilon. I want to show that an converges to a. Sorry about this error. mod an minus a is less than or equal to mod an minus ank plus mod ank minus a. Okay, I have used ank now to anchor the sequence an. Now the first term is certainly going to be less than epsilon simply because that's the way nk has been chosen. The second term will also be less than epsilon because that's the way nk has been chosen again, right? So this whole thing is less than 2 epsilon. Is less than 2 epsilon. So by the k epsilon principle, we are done. We are done. So this shows that a Cauchy sequence is convergent. In the chapter on topology, we will see that Cauchy sequences play a very, very big role. This is a course on real analysis, and you have just watched the module on the Cauchy criterion.